even with the 108 classes, the first time I've not overloaded my courses, because essentially what I'm teaching now is it's almost a new course. I keep saying that, but it's so hard when you've been teaching the same thing since 2016. You gotta change it every semester as things change. You get more information. It's been a little bit different every semester, but it's basically been the same thing. And now it's like calling this thing, that thing, and adding this information and not including this information, and switching the order in which you're teaching it. Like it's throwing me off. So because of that, I haven't overloaded my courses, and I think some of the faculty are upset with me because they're used to it since 2016. I'm like, hey, can you add this person to your class? And I've always said yes, and now I'm like, no. I think I've ruffled some feathers unintentionally, but I have to. This is essentially a new course. Plus the whole thing with doing it online, that's new for me too. It's not like 108.
Because I noticed in the summer they really don't offer too much, in my opinion.
And I travel a lot. Otherwise, I would do one-on-one over the summer. I used to, but now that I travel, I'm gonna do online stuff. And I'll keep pushing for it.
Well, if we can help, we will.
Right. All right. So now we have alert. A little bit extra credit for being here early. We have Ashley, correct? A little bit extra credit for being early. Last one. They get this. Oh yeah, the last one. That's a good hint. So a little bit extra credit for being early. We got Saunders online. So Saunders, I guess we'll just do things you haven't been doing it. So once the class officially starts, I don't know if you hear me. It's not time to start. You might not be here right now, but if you are, when the time starts, when the class starts, just write down those attendance words and make sure you send them to me before 9 a.m.
So I have a question.
Mm-hmm.
Last week I went downstairs. When you get downstairs, there's a room 131. I don't even remember what it's called. Study something. Where is your office?
That's it, 131.
It is?
Yeah, it's got my name on the door.
No, this isn't your name on it. When you go straight down the steps, you turn left. There's another room that has 131. I'll tell you today. I'll look when I get done.
Well, mine is on that side of the building. I said that closest to the.
So you look it down this way down the steps. I went the opposite. Okay.
Glad you asked. All right, that's some guessing games here. Figure out who's who. Mm-hmm. I'll just go for hints. Since you were here first, what's your last name start with?
S.
Still choices there. I would say Shamblin. Look with extra credit for being early. And what's your last name start with? Yeah. Oh, that's right. I knew this. So you're the other Miller, correct? Taylor?
Right.
And a little extra credit for you for being early. It's not much. 2.5 instead of 2.6 points, or 2.4, but it all adds up.
I have another question too. Will you be doing study guides like you did for 108? Because I glanced online, I didn't do anything yet, but on the study guide on there, I noticed a question or two, or specifically what you said wouldn't be on everything.
Well, thank you. Yeah, those have been switched over from the old course, and I've gone through them and tried to get rid of the ones that. Oh, wait. I'm sorry. Yes, that might be on purpose, but I'll double check anyway. So there are some questions where I said it won't be on the exam, but it's still in the study guide. Like, it's not completely useless information, so I still wanted to emphasize it that way. But I'll take a look anyway, just to be sure. And yeah, so the difference between this class and 108, as far as study guides are concerned, is you get points for doing these study guides. Though you get 2 points for independent. So it's handy. I think. And what, another thing I'm gonna do, I do it every semester, it's like, before we take the exam, I'll ask you guys what time you want to meet online, and anybody who wants to meet online for the exam review, that's what we'll do. So I will go through every single question on the study guide. Okay, this definitely won't be on the exam. This definitely will be on the exam. This might be on the exam. This is how I might reword this. You know, this is why this is the correct answer. This is why it's the incorrect answer. That's what we'll do when the time comes. And of course, if technology works, then I'll record it. Anybody who's not in the meeting can watch the video. What does your last name start with? F? Yes. Fisher. Okay, you got a little extra credit for being here early.
Thank you.
And we are recording, so if anybody has any questions, lay them on me. It's good. We can record it and anybody can watch the video and benefit from your questions. I'm still waking up. Sorry, guys. Good weekend. Did anybody do anything fun this weekend? No? Me either, really. Just hung out. Anybody work this weekend other than schoolwork? Like, anybody have like a job you have to do?
Yeah.
Where do you work? Okay. Oh, that's right. I remember, I think you did the online quiz, right? Yeah. What does your last name start with?
See.
C? Oh, that one's easy. So Curry. Okay. And a little extra credit for being early. I just posted an announcement on Facebook. I'll go ahead and tell you guys. There's a lot of people turning things in, so I'm really excited about that. Usually I don't get this many independent work papers turned in. So I have a lot to grade, a lot of emails to do. So please bear with me if I'm a little bit slow to reply to your emails or grade anything you turn in. That's the situation right now. Morning. And what did your last name start with? H. So this one I have choices. I'm gonna go with Helen. All right. Well, so it's Hamilton.
Yes.
All right.
Morning.
Is it Bryant?
No, I'm Norris.
I get it one day. But Bryant usually sits next to you, right?
Yeah,
Okay, so it's
close.
so yeah. Completed. And I assume there's gonna be some people dropping this course, so if you guys know anybody who needs a one-on-one class, maybe they can still add it before it's too late. Love to have some more people fill in those empty seats, so to speak. Good morning. So there's Brian, right? Sure. Like the first thing. Morning. Vargas?
Morning.
It is Vargas, right?
Yeah.
Okay. Sorry. It's all right. We haven't started yet. It's all good. Let's see. Is it Hellman? Garvey? We've got a little bit more than 1 minute left. Does anybody have any announcements? I've already asked if you have any questions. Do you have announcements? Like any kind of sports thing or extracurricular in the club? Need an announcement? All right. Seconds left. And a lot of people, I think, are going to drop this course. Better to drop it early though than wait until the end. Yep, 8 o'clock. So, because I know everybody here is accounted for, but since we're recording, I'll go ahead and say the names that are not here. Make sure I'm not missing anybody. Hellman, Moody, Newsom, Thor, Rollins, Ruffin, Sherman, Taylor Pierce, Thompson, Valdez, Williams, and Winfield. Good. All right. You jump into it. So for announcements, remind everybody that the lab is on Wednesday. So technically the pre-lab was due last night. I'm going to get around to grading them as soon as I can. And the reason I love that we don't have lab until Wednesday is if you have any mistakes on the pre-lab, I can tell you, and then you can fix them. You know what you're doing before we get in the lab. But anyway, yeah, so make sure you do that. Don't forget if you have written syllabus to read the syllabus. We did chapter 1, the study guide. I recommend doing that. You can get independent work points for doing it. Some of you have already done it. I'll try to share an announcement soon where I actually show you where that study guide is. And that's it. And again, I'll remind you, I'll apologize in advance. Basically a new course for me. I'm using a new book, and I like to teach out of the book, so it's throwing me for a loop. So I apologize if I seem out of there. I know the material. It's just that I'm out of my element. So anyway, any questions before we get started? All right, I have a question for you then. How many of you took biology because you didn't want to take chemistry? Oh man, well, we got some bad news for you. We're about to do some chemistry. And also, really, biology is nothing other than chemistry. Really, when you think about it, that's basically what biology is. When you really dig into biology, at the core of it, it's chemistry. So to truly understand everything you're going to learn in this semester, you need to understand some chemistry. You guys see that, or is it too much over there? Anyway, let's jump into it. So these pictures are not from your textbook, they're from your old textbook, but I like it because they started each chapter from your old textbook saying like, hey, why does this matter? To a non-biology major, why do you need to know this? And I like that little, I don't want to call it a guessing game, but that's sort of what it is. I like that they did that. Can anybody tell what that picture is up there? It's a little bit hard to see. Yes, this is what that picture is. What is it? Yes, a coral reef. Good. Now, obviously, we know what that has to do with biology because coral reefs are living. But what do you think that has to do with chemistry? Any guesses what a coral reef might have to do with chemistry? Well, the old textbook mentions the fact that, man, we got all these schools before I done. Should have done this before we started. Anyway, are you kidding me? Whatever. So, your old textbook mentions, like, uses the example, a car in Boston, right? You start the car, the exhaust goes out, and that exhaust out of that car in Boston makes its way down to the Florida Keys. And, oh no, excuse me, your book even says the Great Barrier Reef, which is also true. So basically the point is, chemistry can matter because you can kill stuff, like car exhaust kill stuff. A better example for us would be, the exhaust that comes out of John Amos right down the road, that comes out, goes in the atmosphere and affects the Florida Keys. If you have my 108 class, you know what I'm talking about. And to me, that's a big issue because, we talk about how coal is so good for our economy in West Virginia, but I'm from the Florida Keys. Tourism is so good for our whole economy is based on tourism, right? So the economy of West Virginia kind of destroys the economy of Florida. So it all depends on where you're from. Anyway, how about this? What's this picture of? Well, obviously you can see what that's a picture of. It's fries, but what's this stuff going on top of the fries? What do you think? Salt. Good, salt. And I love that the old textbook talks about this. Does anybody know what the chemical makeup of salt is? What? I think you said sodium chloride? Yes. And what I love about this is sodium is an explosive metal. It's really dangerous. Chlorine, it's a gas, a poisonous gas that we used in World War I to kill people. So separately, those things are really dangerous. Together, they're delicious. And we actually need a little bit of it in our diet. So that's I think it's a great example because there's a lot of chemophobia out there. People trying to scare you from this vaccine or that product or whatever because it's got this in it, don't you? And yeah, that one thing that they say might be dangerous on its own. But with chemistry, those dangerous things on their own become, kind of safe, basically. And another thing I like to point out with salt too is, too much salt's bad for you, right? But you still need some salt. And that's another thing with chemistry. And another way people try to scare you with stuff is they'll say, that's poisonous. And everything's poisonous. It all depends on the dose. A lady just died less than a month ago. I saw it on the news from too much water. She killed herself by drinking too much water. So everything's a poison if you have too much of it, which is a great independent work topic. And I'm going to go through that throughout this chapter. But think about any of these elements I tell you about. Think about them or write about it and see how much do we need? Because you don't have enough of something that's bad for you. How much is too much, right? How much is poisonous? And what happens if you don't have too much or you have too much, right? Anybody know what this is? What metal that is? Yes, it is copper. Not that you need to know that. And that's another good example. You need copper in your diet. I don't know if you knew that. So you could look at like how much do you need? What happens if you have too much? What happens if you don't have enough? So anyway, let's jump into the actual important stuff. Again, this is a new textbook for me. So I'm going to be weaving around and doing things in different orders. But the first thing we're talking about is the building blocks. So you're going to learn about what molecules are. Can you repeat that?
No, you can't.
All right. Let me change this. See what I mean? I apologize, guys. While I'm fixing this, does anybody have any questions? Yeah, there we go. Yes. There we go. We're going to talk about molecules. The first thing is the whole chapter is broken down into 3 chunks, and the first thing we're talking about is molecules. And the learning objectives are going to be able to describe matter and elements. It's probably going to be a review for most of you. You need to describe the interrelationship between protons, neutrons, and electrons, and the way in which electrons can be donated or shared between atoms. So how many of you have seen this kind of material before? Or let me ask you, probably most of you, who has not heard this stuff before? Like protons, neutrons, electrons? No, so this is not new for anybody. That's good. All right, each element consists of one kind of atom. What is an atom? You need to know this for the exam. An atom is the smallest component of an element that retains all of the chemical properties of that element. I think another way of saying it is if you were to break something down, that's as small as you can get. If you break that down anymore, it's no longer an element, right? So if I took gold and broke it down until I got one atom, I can't break that atom down anymore and it'd still be gold. Right? If I were to take away an electron or a proton, it would no longer be a regular atom of gold. So yes, that's the basic unit that we're talking about here. Any questions about what an atom is? It's pretty simple stuff, right? Does anybody know what atoms are made of? As far as we're concerned, they're made of three things. I said them earlier. Does anybody know? Yep, protons.
Electrons.
Good. And there they are. You need to know that too. Atoms are made of protons, electrons, and neutrons. You need to know their charge. Protons are positive. That's easy to remember because it starts with a P, right? And pro, positive. So that's +1. Electrons are negative. That's easy to remember because getting electrocuted is a negative thing, right? Just remember it that way. And of course, neutrons, as the name implies, is neutral. So you need to know all that. In addition to knowing the charge, you need to know the mass. As far as we're concerned, electrons don't have mass. The protons and neutrons both have a mass of 1. Any questions about that? It's pretty simple stuff, right? Stuff you've all seen before, I'm sure. The relationship between protons and electrons here is if the number of protons equals the number of electrons, then the net electrical charge of that atom is 0. Or even that molecule, whatever. It's 0. If the number of protons equals the number of electrons, it does not have a charge. And then the atom is said to be neutral. Those are just some examples at the bottom. Hydrogen has 1 proton, 1 electron. That gold has 79 protons and 79 electrons. Therefore, those are 2 neutral atoms. Those are just examples. You don't need to know anything about hydrogen or gold necessarily. You probably get tired of hydrogen. We'll talk about that a lot. But are there any questions about what's on this slide? All right. So next thing I'm going to talk about is the nucleus. Right? We're going to talk about how it's put together. Of these 3 things, does anybody know what's inside the nucleus of an atom? Or I guess which one is not inside the nucleus of an atom? How about that? Any guesses? Wait, someone's got to guess. It's okay to be wrong. You guys, technically, as far as I'm concerned, it's the first time you've seen this. So which one of those do you think is not inside the nucleus of an atom? For 1 point of extra credit.
Neutron.
What is it?
Neutron.
Neutron. Good guess. That is incorrect, but you still get a point. So when you email me today, or if you email me today, remind me that you got an extra credit point. So speaking of emails, the first word for attendance is going to be coffee. So if you're online, I know there's one person online right now live, you're going to send me those words. Once I'm done with the class, sometime between when the lecture's over and 9 a.m., send me those words. And if you're watching the video, then it's a whole different story. Anyway, yes, so the nucleus is the central core, and the protons and neutrons are in the nucleus. You need to know that. And that uranium, that's just another example. You don't need to know anything about uranium. But what charge did I say protons have? Good, positive. Now look how tightly those things are packed together. Have you ever tried to put a magnet together when it's like the same, the plus plus and the minus minus? What happens when you try to do that? Right, they repel each other. Same thing here. Protons repel each other. Electrons repel each other because they have the same charge. So imagine, the book doesn't really talk about this, but it's worth mentioning. Imagine how much energy it takes to keep all those protons together because they don't want to be together, but there they are packed together and tightly. That's a lot of energy, right? And that's the basis of like a nuclear bomb. Because you split that, right? All that energy that's holding those things together that don't want to be together, that energy is released. And even though we don't talk about that in this class, that is basically how we talk about energy as far as the stuff you're going to learn in the upcoming chapters when we talk about breaking down molecules and releasing energy. We'll talk about it with protons, but that's still the same basic concept. However much energy it takes to keep something together, once you break that thing, that's how much energy is released. Anyway, any questions about what's in the nucleus of an atom? So again, we have protons and neutrons in the nucleus. So by definition, what is orbiting around the outside of the nucleus? Electrons, right? The third thing. And there you go. That's what it looks like. That picture's not from your textbook, but I like this picture better, right? So here's helium, 2 protons, 2 neutrons in the nucleus. And I like the way this picture is because it's more like a cloud. Yeah, you can see the 2 electrons, but it's a cloud. Not that it matters at a 100 level non-biology major course, but a lot of times you see pictures, and I'll even do this in lab. You'll see pictures of rings of electrons, and that's good for our purposes, but in all actuality, they don't actually travel in rings. It's more like that's the cloud of the probability of where you would find an electron. Anyway, any questions about protons, neutrons, electrons, nucleus, anything like that? Okay. Atoms of an element have the same unique number of protons. You definitely need to know that. Another way of saying that is you could say an atom or an element is defined by its number of protons. The number of protons determines what element it is. And there's a periodic table up there behind you guys. Starting at the top left, if you read it like you would anything else, and go left to right, top to bottom. That's how it works. So you have 1 proton, and then 2, 3, 4, so on and so forth. So helium is the one on the very top left because it has 1. If you add another proton to, did I say helium? Hopefully I said it correctly. Hydrogen is the one on the top left. I'm reading helium. Hydrogen is the one on the top left that has 1 proton. If you add a proton to hydrogen, it is no longer hydrogen anymore because it has 2. Therefore, it will be helium. And that's just an example. You don't really need to know that about helium or hydrogen. But I'm telling you, what you do need to know is the atomic number. That's what defines the element. It's the number of protons. And then a related number that you need to know is the mass number. That's basically how much it weighs. And it's simply the sum of the protons and the neutrons. So for those of you who have done the All About You quiz, I know a lot of you said math is your hardest course. You don't like math. You're not good at math. And I wrote back and said, don't worry, there's not much math in this course. And I stand by that. There's not much, but this is the extent of the math in this course. So you will get a question to someone on the study guide where it says, all right, this element has this many neutrons and its mass number is this. So how many protons does it have, right? So you know that the mass number, what we have, protons plus neutrons equals mass number. Right? So you'll get a question where I give you maybe the number of protons and then mass number. So then you have to figure out the number of neutrons. Maybe I'll give you the number of neutrons and you have to figure out the number of protons. So it'll be really simple like that, right? So it might be something like this thing has 5 protons and its mass number is 10. How many neutrons does it have, right? So, 5 plus what equals 10? 5 plus 5 equals 10. So it'll be nice and easy like that. Make sense? Any questions about that? All right. So we've talked about the mass number. We've talked about the atomic number. That's the element symbol. You don't need to memorize any of these. There'll be nothing on the exam where I say, just give you an element, say, what's its symbol? What's its mass? What's its, any of that. But I'm not going to ask you those questions. You don't need to memorize any of this. The only thing we haven't talked about this, though, or the only thing we haven't talked about yet is the atomic mass in ANU. So that's where it gets a little bit more confusing. The atomic mass is not the same as the mass number. And I'm going to explain it because your textbook doesn't. It's there. Your book says what the atomic mass is, but it doesn't really explain it. So I want to explain it so you understand why it's different. So like I said, it's similar to the mass number. If you can look up there, I don't know if you can see at the top left, hydrogen with its atomic number of 1 has 1 proton, but its weight, its atomic mass, is 1.008, I believe it is. I don't have it memorized. But it's not 1. Oh, it's right in front of me. 1.00784, right? We can round it up to 1.008. So where does that come from, right? I told you that protons weigh 1, neutrons weigh 1, so where are we getting decimals from? And it's basically because it's an average. So what this means, there are, first of all, let me back up. There is no hydrogen, for example, that has a mass of 1.00784. That's impossible, right? Because it's going to be whole numbers. There is no one hydrogen that has that mass. But in nature, there's a lot of hydrogens that have just the one proton. Then there's some that have one proton and one neutron. So it's that one's atomic mass would be 2. This one will be 3 because it's one proton and 2 neutrons. So it's like an average. They take all the hydrogens that we think of that ever existed or that do exist, and we average them up. Like, for example, how many humans, what's the average number of fingers for a human? Does anybody know that? No guesses? Actually, I don't know it either. You could look it up for independent work, but it's probably not 10, right? It's probably 9.999 or something, right? 'Cause some people are born without fingers, but missing a few. Or actually, some people are born with extra fingers, but the point is, right? You know, that's how we get there. It's an average. Right? If you take all the humans, like, all right, they have 10 fingers, 10 fingers, 10 fingers, 10 fingers, 9 fingers, 10 fingers, 10 fingers, 10 fingers, right? You average that up, and you would get 9.9999, whatever. And that's where the atomic mass comes. And the only reason I wanted to explain that to you, because I'm not going to test you on it, I just don't want you to get confused when you see the atomic mass, back it up, and the mass number. I just want you to know those are different things, and don't let them confuse you. Any questions about the atomic mass? All right, let's talk about the periodic table of elements. I'm not going to probably ask you any questions about this, but it includes the atomic number and the atomic mass of each element. Again, there's one right behind you. You can take a look. It provides key information about the properties of elements. For you, it's not even important, but for people doing real chemistry, so to speak, it is important because you can tell by where it is on the chart, on the table. You can tell things about how it's going to react, things like that. Shows how electrons are organized. We'll get into that later. The few things you need to know about that. We'll talk about that when we cross that bridge when we get there. It provides important details about how the atoms will react with each other. Again, if we were doing some real chemistry, that would be important. If you were a chemist, that would be important. But we're not. You're just learning the basics of chemistry. So, in my opinion, that's not very valuable information. And I'll show you a picture of the periodic table on the next slide. But are there any questions about this? And again, if you take notes, I wouldn't even write any of that down because I'm not going to ask you anything about that. But there it is. That's the periodic table. And again, if we were doing real chemistry, this would be interesting. So these all have one electron on the outermost ring, which is handy if you're trying to determine how they're going to react. But we're not going to be doing that in this class. These all have a full outer ring. So we know, generally speaking, they're not going to react. And we'll get back to that later. Who knows what an isotope is? That's the next concept that we're going to learn about. Any guesses about what an isotope is other than the baseball team on The Simpsons? No guesses? All right, you will need to know this. Well, first of all, before I tell you what an isotope is, let me remind you what I said about protons, right? If you change the number of protons, you change the element. So we have a hydrogen with its one proton. If you add a proton to it, it becomes helium. Nitrogen, right? If you were to take away a proton, it would become carbon. So if you change the number of protons, you change the element. That being said, let's talk about what an isotope is. It's different forms of the same element, or what you need to know is if you change the number of neutrons, then you've made yourself an isotope. In my opinion, that's all I would write down for that. And I'll put it right there next to the proton. If you change the number of protons, you change the element. If you change the number of neutrons, then you have an isotope. So it's still the same element. It just has a different weight. And that goes back to what we were talking about with the atomic mass, right? Like I said, some hydrogens have one proton. Some hydrogens have one proton and one neutron. Some hydrogens have one proton and two neutrons, right? Those are all different isotopes. They have the same number of protons, so they're the same atom, the different number of neutrons. I wish I could get them to give us some heavy water. I'm going to request that. That'd be great in this class, in this lecture, to pass around a thing of heavy water, because it's water that has heavier hydrogens in it, and you can feel the difference. You can feel how it's heavier than regular water. I think that'd be good. Anyway, that's what an isotope is. These are just examples. You don't have to memorize anything. I don't even think that's for your book. I found that somewhere else. But these are different isotopes of carbon. Carbon 12 was the normal one. Carbon 13, carbon 14. You know, you can see The number of protons stays the same, but the number of neutrons is different. Because again, that's what gives us an isotope. Any questions about isotopes? Well, since I just said it, the next word for attendance will be the Simpsons. Like Homer Simpson, Marge Simpson, Bart Simpson, that whole group. All right. There's no questions about this. We'll move forward. Make a good time. This is important information, this chapter, but it's, in my opinion, pretty simple, straightforward stuff. So here's some more examples. There we go. Again, I'll just use the carbon as examples or isotopes. This goes back to what I was saying earlier, like how many fingers does the average human have? I think that's actually a fake picture, but still it drives home the point, right? Not everybody has 10 fingers. So the average number of fingers for a human is probably not 10. It's probably really close to 10, but not 10. I'm not going to ask you anything about this. This is not important as far as I'm concerned. You can brain dump this and understand everything else I'm going to teach you throughout the semester, but it's out of the textbook, so I'm teaching it to you very quickly. We already know what isotopes are, right? You change the number of neutrons, then you have an isotope. What's a radioactive isotope? It's an isotope that's radioactive. In other words, it's unstable because its nucleus decays spontaneously to become more stable, right? It's got too many neutrons in there, so it's just giving stuff up. And the only reason I guess it's even worth mentioning, other than the fact that I teach out of the textbook, is this is what we use for carbon dating. And I'm not going to ask you anything about carbon dating. Carbon dating is not important for your non-biology majors, but the information there if you want to read about it. Basically, we know how much, like, the percentage of carbon-14 is very small, right? We know what the percentage is right now. So when something dies, we know how much of the carbon should be carbon-14 as opposed to carbon-13 or carbon-12. But as it decays, we know exactly how long it takes to decay. So we can look at something and then look at the ratios. Like, all right, how much carbon-14 is there versus regular carbon? And then based on that ratio, we know how long it's been decaying. That makes sense? Not that you need to know that, but that's how it works. It's a good independent work topic too, if you want to look more into it and write about carbon dating and how it's used, because there is a limitation. I mean, look, the half-life is 5,730 years. So, for example, if you're looking at dinosaurs, that's completely useless, right? They've been dead a lot longer than that. So that's some other stuff you could look up for independent work. How else do we date things other than carbon dating? Because it definitely has its limitations. Anyway, any questions about this stuff that I'm not going to ask questions about? All right. This goes back to what I was saying. Those little blue dots represent the number of carbon-14s, the ratio of carbon-14s, and exactly the ratio changes as time goes on, and that's how we use carbon. All right, let's talk about chemical bonds. This is an important information. You're going to get really familiar with this in lab next week because this is when we're going to do this. But it's only the electrons that are directly involved in chemical reactions as far as we're concerned in this class. It's all about the electrons as far as we're concerned in this class. Not that I'm going to ask you that. That first bullet point won't be a question. That's just a segue into what I'm about to teach you. We'll be doing stuff. It's the number of electrons that determines the chemical properties. Also, you don't need to write that down either, because what you need to know is how the number of electrons determines the chemical properties, and it's this right here. If you're writing stuff down and you're a note taker, this is the information you need. Again, we draw it in rings and we talk about it in rings. For the purposes of this class, that really works. So as you're learning this, please realize too, just keep in the back of mind in real life, they're not actually in rings. This is just the best way to teach it. But anyway, for all ones on the table, as far as we're concerned, the inner ring holds 2 electrons. So if something has 2, like helium, for example, it only has 2 protons, therefore 2 electrons. That's why it's not reactive. Because that inner ring, for it, the only ring, it has 2 electrons. So it's stable. It doesn't want to give any electrons up. It doesn't want to take any electrons. So it's stable. And as far as we're concerned, and this is not necessarily true either before our class, everything else, you've got that first ring. So once you go down to 3 electrons, for example, now you're going to the next ring, right? As far as we're concerned, the outermost ring holds 8 electrons. And that is definitely a number you need to know. Actually, they both are. Technically, it's 4 pairs of electrons, but I don't care that you know that. Because again, this is a 100 level non-biological major course. But you definitely need to know that first ring holds 2, the outermost ring holds 8, as far as we're concerned. And if you want for independent work, you can look into that and find out the truth behind that. Because what happens is, you have your first ring, then your second ring, and then as obviously the more electrons you get, you keep going up and up and up. And eventually the whole number 8 rule isn't true. And look that up if you want for independent work. As far as we're concerned, that's what you need. And then this, again, you need to know this. The full ring means it's a stable atom. It has a full ring, it doesn't want to give electrons, it doesn't want to give electrons, it's happy where it's at. So you're going to be doing things in lab next week where I tell you an atom and I give you its atomic number. And from there, you need to figure out how many electrons it has, right? And if the electrons equal the protons, it's the same number. And then once you figure out how many electrons it has, then you can determine how many times it's going to bond. And I think I have this on the next slide. Nope, I don't have it on the next slide, so I'll go ahead and show you. I use carbon as an example. Can anybody look behind you and tell me what the atomic number of carbon is, or if you just happen to know it? That would be impressive. So can anybody see the atomic number for carbon? I think I heard you say it. Good, 6. Meaning it has 6 protons. So if I give you, and you will have to do this in lab next week, if I say, all right, here's carbon, tell me how many electrons it has, right? So you know its atomic number is 6, therefore I didn't say anything about it being charged, so it must have 6 electrons. So I'll draw it. So the first ring holds 2 electrons. So let's see, we got 6 total. I've already done 2, so we need 4 more. 1, 2, 3, 4. Let me double check my math. 1, 2, 3, 4, 5, 6. All the electrons are accounted for. Here we have 4 electrons on the outermost ring, but I said it needs 8. Therefore, I know this thing needs somehow to get 4 electrons to have a full ring. Does that make sense? Because if it had 4 more electrons, it would have a full ring. So carbon, we now know, can bond 4 times. And if you're taking notes, just don't need to write that down because I don't want you to memorize the fact that carbon can bond 4 times. I want you to be able to figure it out. If I were to give you an element and say this is its atomic number, how many times can it bond? So, any questions about this? All right, so like I was kind of getting at with this bullet point here, it's these chemical reactions that enable these atoms to transfer or share electrons, right? It allows them to get to that stability, to get these 4 extra electrons in the case of the carbon, right? And because of that, when they're giving up electrons or they're sharing electrons, they stay close together. And that right there is what's called a chemical bond. Yeah. So any questions about that? That's why we have chemical bonds. It's all about the electrons. All right, if there's no questions about that, let me give you some information that's not in your textbook. So I'm not going to test you on it, but these are words. I don't know why your textbook didn't include this, because these are words that we use, especially in labs. So you need to know what these words mean, not because I'm going to test you on them, but because we're going to use them. Anyway, cells constantly rearrange molecules and they break bonds to form new ones. That's really important, actually. It's the basis of life. Without all those chemical reactions, we wouldn't be alive. So the way your old textbook defined chemical reactions is it's the change in chemical composition of matter. Again, I'm not going to test you on it because it's not in your textbook. It's a 100 level course. So, but this is a good example. How many of you have ever been injured? I got a little cut or scrape or whatever, and put hydrogen peroxide on it. A few of you. All right. What happens when you do that? Like, what's it look like? Burns. It burns, right? What does it look like? What does it do? It bubbles, right? And this is why, right? So this is what hydrogen peroxide looks like. It's 2 oxygens and 2 hydrogens. But when it hits the, your body and it goes through chemical reaction, it produces water and oxygen. Bubbles, right? Water and oxygen. Point being here, what we have here is 1, 2, 3, 4 oxygens, 1, 2, 3, 4 hydrogens, right? We have 4 oxygens, 4 hydrogens here. And then it goes to the chemical reaction and we have 1, 2, 3, 4 oxygens, 1, 2, 3, 4 hydrogens. So my point here is with chemical reactions, we haven't changed the number of elements, right? They're still there. They're all accounted for. We just changed the way they're put together. And your textbook doesn't harp on that, but I think it's important. It's important to know. Not because I'm gonna test you on it, it's just important to know. Anyway, when we talk about chemical reactions, we have reactants on the left, products on the right. Again, I'm not gonna test you on that, but those are words I'm going to use, so you need to know what they mean. And I just said reactants on the left, products on the right. That's only true for this class. It's not always like that. Sometimes this arrow right here can go both ways. But as far as we're concerned, it's reactants on the left, products on the right. So any questions about this? All right, the next word for attendance is going to be cut. Like you got to cut and you put some hydrogen peroxide on. Now back to the textbook information. So again, these atoms, they want to have a full outer shell. So if they do that, if they give up an electron to accomplish this, or they take electrons to accomplish this, then they become electrically charged. And you kind of already knew that, even though I never said it in those words, because I told you earlier that if the number of protons, the number of electrons equals each other, then it's not charged, right? It's a neutral atom. But here, the opposite is true, right? If you have extra electrons or fewer electrons, then you become charged. And that gives us an ion, and you need to know what an ion is. So there, now we've talked about all three. If you change the number of protons, you change the element. You change the number of neutrons, you have an isotope. Now I'm telling you, if you change the number of electrons, then you get an ion. And an ion is an electrically charged atom or molecule as a result of gaining or losing electrons. Which makes sense, right? Because again, if you were to lose a proton, sure, then obviously that would change your charge. But like I said at the very beginning, you change the number of protons, you change the element. So I might ask for this, I might not. Ions are broken down into two categories. You have cations and anions. The cat one is positive, the an one is negative. I might ask you that, I might not. Probably not. We won't, I probably never will use those words again in this course. Now, ions I'll talk about a lot, but you know, there you go. What you do need to know, and somehow people mess this up, I see how they mess it up, but if you gain electrons, then you become more negative. And I think what that confuses people, because usually when you think of gaining something, it's like it's a plus, right? Like you gain more money, you have more, well, plus, right? You have more money. And what makes it difficult for some people is when you're gaining electrons, you become negative. Remember, electrons are negative. So if you're getting more electrons, you become negative. And obviously the opposite is true. If you're giving away electrons, then you become positive. So if this happens, if something gives away an electron, it becomes positive, and then it gives, it gives it to something else right next to it, and then it becomes negative. What happens to negative and positive things? They're attracted to each other, and that is what an ionic bond is. You need to know what an ionic bond is. Of course, it's in the name, right? It's the bond between two ions. But for shorthand, if you're taking notes, I would write ionic bond equals the giving up or taking electrons. Because later you're going to learn about one where you're sharing. An ionic bond, you're giving up or taking electrons. You're not sharing them, getting rid of or taking some. Any questions about ions or ionic bonds? Okay. The next slide, I'm going to show you an example. This picture's not from your textbook. There you have sodium on the left, chlorine on the right. Look at this. Sodium, its outermost ring, it has one electron. How many does it need to be full? How many does any need to be? Like, what's the outermost ring supposed to have? How many?
8.
Good. 8, right? So this thing can either gain 7 electrons, that's not very efficient, or they can just get rid of that one, and then the next ring, it's already full, right? So it does. It just gets rid of that electron. Chlorine has 1, 2, 3, 4, 5, 6, 7. So it just needs one more. So there you go. Sodium's like, look, I'll hook you up with an electron. You need one, I need to get rid of one. It does that. And then what happens? What charge then? This is going to be on the next slide. What charge do you think sodium is once it gives up that electron? It's giving up an electron. So what charge must it become? Good. Yes. Therefore, the chlorine becomes negative. Positives and negatives subtract. And there you go. Sodium chloride. That's table salt. Any questions about that? If you download the PowerPoint, actually I need to fix it. I just looked at it today. The PowerPoint that's on WVSU Online is actually the old version, so I need to change that. But anyway, it does have this video in it. If you download the PowerPoint, you can watch this little video that shows the electrons being given up. So if there's no questions about ionic bonds, let's talk about the next one. Covalent bonds. So if an ionic bond, you're giving away electrons or taking them, what do you think covalent bonds must be? What's going on with the electrons here? Remember, it's all about the electrons. So you're not giving up electrons, you're not taking electrons, so what must you be doing? Sort of, yeah. What about this covalent? The co is a hint. So is it? Oh, right. Well, all right. Well, what happens if you are, like, if your parents are divorced and you're co-parenting? What does that mean? You're co-parenting. Helping, good. Yeah, I like that. That kind of goes along the lines. Or what happens if you cohabitate with somebody? Does you guys know what that means? Like, how many of you live in a dorm? Yeah, and you have roommates. That's you cohabitating with somebody, and then you're sharing a place, right? You're sharing habitat. So covalent is all about sharing. You need to know that. Covalent bond is when atoms share the electrons. They're not giving them up. They're not taking them. They're sharing them. This is the strongest and most common bond in biology. The fact that it's the most common is not important. The fact that it's the strongest is important, because when we talk about DNA, that's going to be an important fact. Covalent bonds are the strongest bonds. You need to know that. Technically, when this happens, right, when you have two atoms come together in a covalent bond, then what you have is a molecule. I'm probably not going to ask you the definition of the molecule, but I'm definitely going to use the word a lot, and it would help if you know what I'm talking about. So that's what it is. We have these atoms that have come together and they're sharing electrons. They're in a covalent bond. That is a molecule. And again, they're still just trying to fill out their outer shell. So again, I didn't erase this. We have carbon, right? Carbon needs 4 electrons to be filled. That's how we know it can bond 4 times, because it needs to share with 4 different molecules. Leave it at that. So that's not 100% true, but for now, that's fine to say. There's 2 types of covalent bonds. There's nonpolar and polar. You will need to understand this too, because there's some other bond I'm going to teach you about. So you need to know the difference between polar and nonpolar. So when you think about like a magnet, it's polar, right? Because there's a positive side and a negative side. Same thing with molecules. If there's a side that's slightly positive and a side that's slightly negative, that means it's polar. And I'll give you some examples on the next slide. But yes, definitely know that. Polar, like if you have a molecule that's polar, again, one side of it's going to be slightly positive, the other side's going to be slightly negative. That will be important later. For now, I'm just giving you that information. So, any questions about that? All right. Obviously, you don't need to memorize the structure of formaldehyde, and obviously casualdehyde is casualdehyde is something we got to put. Those are just examples. Again, talking about covalent bonds. I already have carbon on the board, but it's on the next slide. Its atomic number is 6. Therefore, how many protons does it have? Good. Therefore, how many electrons does it have? Because I didn't say anything about it being charged. Good. Therefore, it has 2 on the inner shell, 4 on the outer shell. It needs 8, right? So it needs 4 more to fill the outer shell. Therefore, they can bond 4 times. Those are the kind of things you're going to be doing in lab next week. Anyway, any questions? And again, carbon's just an example. Don't memorize this. I don't want you to memorize any of this. I want you to be able to do it yourself. If I give you the element, you should be able to look at the periodic table of elements, figure out what its atomic number is, and then from there, figure all the rest of this out. So if there's no questions, here's some pictures from your old textbook. There's different ways of drawing molecules. You don't need to memorize any of them. The point here is, you might see any of these. So it might confuse you. Like if you read something, you look up something, and you're like, all right, this is what formaldehyde looks like. And then you look at the textbook and it looks like this. You're like, what? Are we talking about different molecules? No, it's just different ways of drawing. That's all the reason I'm bringing it up. You don't need to memorize this. Just don't want you to get confused or think something's wrong when I'm teaching you about a molecule. And it looks like this in your textbook, but then if you look at mine, it looks like that. Right? There's just different ways of drawing. And this is the way that you're going to be familiarizing yourself in lab. You're going to be drawing molecules. That's the other part of what you're going to be doing in lab, drawing molecules. So I'll give you the chemical formula. Like this would be COH2, right? Now that's all I'll give you. This. Well, I already have it there. COH2, right? And given that, you're gonna have to draw all that, but I'll teach you how to do that. Any questions? Okay, you can download the PowerPoint. Again, this little video you can watch that shows an animation of covalent bonds. Now let's go back to this idea of hydrogen, or excuse me, jump there. Polar bonds, right? Or polar molecules, like we already said. If it's polar, that means half of it is, or part of it is slightly positive, part of it's slightly negative. You need to know that. It is an uneven sharing of electrons. Water is a great example of it. I know you guys, it's hard for you to see, but for those of you in the back, can someone tell me the atomic number of oxygen? Or you can look it up, whatever. Atomic number of oxygen. Good. Its atomic number is 8. Therefore, it has how many protons? Good. 8 protons, right? All right. Now, can somebody tell me the atomic number of hydrogen? 1. Good. Therefore, it has how many protons? 1. Good. So if we have this water molecule, this thing has 8 protons. 8 of them. This thing only has 1. And what charge are protons? That's definitely information you need to know. What charge are protons? Positive. Good. And what charge are negative? Or what things are negative? How about that? Electrons, right? So if you're an electron, you're attracted to protons, right? Because the negatives and positives attract. So if you were an electron and you're getting shared between this oxygen and the hydrogen, you can't escape it. You get shared. Which one are you going to want to hang out with more? The oxygen or the hydrogen? Remember, you're an electron. You're negative. You want to be around positive things. So we're going to be hanging around the oxygen or the hydrogen more. Oxygen, right? Because it has more positives, right? So because of that, oddly enough, the water molecule is slightly negative on this side, slightly positive on this side. Because the electrons are being shared unequally. Make sense? Technically, that's not even the right symbol. Technically, there should be a symbol that indicates that it's slightly negative and slightly positive. The way I've drawn it technically says that's fully negative and fully positive, but for this course, that is okay. Anyway, that's an important thing. Any questions on what makes a polar molecule? So let's talk about why is that important? Because there's a third bond that you need to know about. So we talked about ionic bonds, we talked about covalent bonds. Let's talk about the next one. Hydrogen bonds. It's the weakest of the bonds, and you definitely need to know that. That will be important later in the semester, just like covalent bonds being the strongest will be important later in the semester. These are the weakest, and that will be very important. And as far as we're concerned, I mean, there's other molecules that do this too, but as far as we're concerned, it's all about the attraction between water molecules. That's all we really care about. So this one water molecule, those are covalent bonds keeping it together, right? That hydrogen is covalently bonded to that oxygen. That hydrogen is covalently bonding to that oxygen. But I'll show you on this next slide. We're talking about the attraction between other neighboring water molecules, like this one to that one, this one to that one. Those are hydrogen bonds. Remember, that's a slightly negative end of the molecule. Therefore, the slightly positive end of another water molecule will be attracted to that slightly negative end. And that's what a hydrogen bond is. You need to know it. It will be important. No need to memorize the fact that the oxygen is a slightly negative part, hydrogen is a slightly positive part. It doesn't matter to me. Just know that they are slightly charged, and therefore they're attracted to each other. And that will be really important later when we talk about why water is so important. Like we all know we all know water is important. We'll learn later why. And it almost all has to do with those hydrogen bonds. So the next word for attendance will be water. Knock this out before class is over. Let's talk about this. You do not need to know this, but it's also not in your textbook. There are 92 naturally occurring elements. You can see those on the top of the periodic table. Your old textbook gave those examples: carbon, oxygen, potassium, gold. Each one has a symbol derived from English, Latin, or German. Again, that's not in your textbook, so I'm not going to teach you. Here's also something not in your textbook, but I want you to know this. So if you're taking notes, take this down, because it's not in your textbook. There are 25 elements. So of those 92, there are 25 that are essential for our survival. Just know that there are 25 of them. They're called essential elements. You'll figure, right? And that's a great topic for independent work. You can look any of them up. Like I said earlier, find out how much is too much, how much is not enough. What happens if you have too much? What happens if you don't have enough? Where do you get them, right? Like in your diet, where do you get these things? Another thing that your book doesn't mention, but I want you to know, is I call them the big four. And after lab, next week, you probably have no problem memorizing this because you're going to draw them a lot. You need to know what I call the big four: oxygen, carbon, hydrogen, and nitrogen. Know the big four. Very important. And yes, like it says up there, that those four make up about 96% of what you are by weight. It's those four. I don't necessarily want you to memorize that number. It doesn't matter. Just know the large majority of what makes you up is those four. And also, you know, obviously we're talking about humans, but this is also the big four for most living things. Most things that are alive, that's the big four. Obviously the percentage is going to be different, but those are the big four for most living things. Any questions about that? All right, I'm going to fly through this next stuff. Again, it's not in your textbook, so I'm not going to ask you about it. I will ask you this. This other stuff I won't. It's just good for you to know. So like I said, about 96% of you is those big four. So what about the other 4%? Most of the other 4% is these 7 elements: calcium, phosphorus, and again, the old textbook told you why it's important, where you can get it. You can look all these things up. Actually, I'm not even getting into it. So you can look up the other one. What are the other 5? Right? So you got calcium, phosphorus. You can look it up for independent work. You don't need to know it for the exam. And then we have something called trace elements. These are the really interesting ones. There's 14 of them, and less than 0.01% of your weight is made up of trace elements. These are the ones that are really important as far as like the dosage, right? Too much of it can kill you. Not enough of it's bad for you too. Iodine is one example. Not that you need to know that. None of this is in your textbook. Fluorine is a great example. People will say, "Oh, I can't believe you drink the city water. They put fluoride in there. Fluoride's a poison." And it is if you have too much of it. But you're not getting too much of it. I guarantee it. I shouldn't guarantee it. But I'm willing to bet a lot of money. But anyway, those are just some examples. You can look up the other trace elements. I love this. Iron is a trace element, like literally the metal iron. So when you see something that says it's iron fortified, it is because there's metal. But you need it. You need it for your blood. If you were to take that, and you can click either one of these, and there's a video. If you take that and blend it in a blender, so it's just a big wet mush, like with some water, then you put a magnet to it, the iron from the cereal will stick to the magnet. There's literally iron in your food if you need it. And that is where we will end for today. So see you on Wednesday. Don't forget to do a little extra credit. We're at WBS. You can hear on Wednesday. If you wrote down those attendance words, make sure you send them 0.9 AM for a little extra credit.